All right, hello everybody. So here we're going to look at the Quickselect algorithm, which is a sort of close kissing cousin to Quicksort here. So the selection problem, and that name coming like sort of like from selection sort is not a coincidence. The selection problem is the problem of we want to find the kth smallest or largest, right, value in an unsorted sequence. So like if k is 0, then we're looking for the smallest value. If k is 1, we're finding the second smallest. If k is n minus 1, the size minus 1, then we're finding the largest value. That's the selection problem. Okay. Now, of course, if the sequence is like already sorted, then the kth smallest element is just in index k. Like that's easy, right? So we've seen a couple of ways that you could solve this problem. One would just be like, okay, sort it and then just look in index k, like that would sort of work. But that requires you to do a full sort, running in ideally like something like n log n time there. Another option would be we could take selection sort, which is based on the selection problem, and run the first k plus 1 passes. So that will only sort the sort of first k many elements, and then we can just return the other one that we want there like that. So that would have a runtime of like k plus 1 times n. So the smaller k is, the faster this is going to run, but with a worst case of O of n squared time there. So can we do any better for the selection problem? It seems like we should be able to do better than either of these two things here like that. So here's an example, right? Let's say we have an unsorted sequence of size 8, and we want to find the third smallest value. Since we're using zero-based indexes for k, right, that would mean that k is equal to 2, right? So just note that that number is 12 for this sequence here. So in terms of what we've got, it would be negative 34 is smallest, negative 12 is second smallest, and then 12 is the third smallest there. So the idea is let's use Quicksort's partition algorithm to partition this sequence. Pick any pivot you want, but we'll use a pivot of 23, and that will give us these two partitions here like that, right? So here is the left partition, and here is the right partition there. So which partition does the kth smallest element lie in? Where's 12? It's here, right? It's in the left partition. So the idea is if k is less than mid, where mid is the return value of the partition function, right? So we do mid equals partition, blah, 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 like that right there. If k is less than the mid, then the value is in the left partition. And if k is greater than or equal to mid, it is in the right partition. So then we just recursively repartition the indicated partition. So unlike Quicksort, where we would do both, here we're only going to do one of them. We're either going to go left or right, but we're not going to go in both directions there. So if we do it again, we're doing repartitioning the left partition. Let's say we pick negative 12 as our pivot there like that. So then that gives us these partitions. This is my left partition here, and this is my right partition over there. So in this case, we would have mid equal to 1. So k, right, is greater than or equal to mid. So that means we should search for the kth smallest element in the right partition here. Now here we have to make a small adjustment. We have to tweak k, because within this right partition, right, the kth smallest value, 12, is no longer the third smallest value. It's the second smallest value, because negative 34 has been eliminated from consideration. So when we go right, we have to apply this adjustment to k to take into account the fact that we've eliminated some of the values, and therefore k is not quite what it was when we started there. So this is the Quickselect algorithm, which is really similar to Quicksort, just with like an if down at the bottom here to determine which direction to go there like that. So our base case is if the size is 1, then that one element is the kth smallest and kth largest and everything in between there like that. Or otherwise, we have to do the recursion there like that. So we partition, get our midpoint, we do the fix for empty partitions if that gives us that, and then we check to see where k lies relative to those two halves there like that. K is less than mid, we go left. If k is greater than or equal to the midpoint, then we go to the right, like that. This is linearly recursive and tail recursive, which means that you could write a loop that would do the exact same thing here like that, right? In fact, if your compiler is in a good mood, it may very well just generate the loop for you from the recursive definition there. Well, in fact, here's a loop-based version right now, right? So here we're just using a while loop based on n, the size of the sequence here. So again, we do our partition, fix empty partitions there like that, right? If we're less than the midpoint, then all we do is we adjust the size to go left. If we want to go right, then we have to adjust the sort of starting point and the size and k, all there like that. And then when the loop terminates, the one thing that is left is the thing that we are looking for there like that. So one part of Quickselect that might be a little bit surprising is it changes the input sequence pretty dramatically, right? So like you could write a function smallest that finds the smallest value in a sequence, and it doesn't modify the input sequence at all. But because Quickselect is based on partition, partition is going to rewrite the stuff in the sequence. So Quickselect has kind of like this side effect of partially sorting the input sequence, or at least the parts of it that we look at there. You can write a non-destructive version of Quickselect here by writing a not in place partition function that would need like an extra O of n sort of temp space to store the partition that we're working on there like that. And also because Quickselect is based on partition, it has the same sort of like, how do we choose our pivot issues as Quicksort? So we're probably picking a random value for the pivot, or picking 3 random values and using like median of 3 there like that, right? If we want to analyze Quickselect here, we have to kind of like look at how are the partitions balanced, same as with like Quicksort. So if the partitions are roughly balanced, like their size divided by 2 all the way down, then we would have this kind of sum. So at the first one here, we look at our sort of like partition has to look at everything, but then in the next step, it only has to look at half the things, and then 1/4 of the things, all the way down to we're only looking at one thing there like that. And this sum here is going to have log base 2 of n sort of terms in it there. This sum is going to be sort of approximately 2 times n minus 1. If n is a power of 2, then it's going to be exactly that there. So if you throw that inside of a big O, you just get O of n there like that. Now again, just like with Quicksort, we could get unbalanced partitions out of this here. So if we're getting unbalanced partitions, then our sum would look like this: n minus 1, n minus 2. We've seen that sum before. That's n times n plus 1 over 2. That would give us a runtime of n squared there like that. So our best case runtime is O of n. And again, it's pretty easy to get that. Just pick random pivots or use like the median of 3 there. But if you're extraordinarily unlucky or you're not very smart about how you pick your pivots, you might end up in quadratic time land. Note that in neither case does the runtime depend on k, right? So whether you want the smallest value or the largest value, or if you do like k equals n over 2, that gives you the median, right? Like that doesn't affect the runtime at all there. The runtime is affected by the size of the sequence and how well you sort of choose your pivots there. So that's Quickselect, right? Kind of a little interesting variation on Quicksort there. I don't know, I thought you might like to see it. See you next time.